Hello, everyone. Today, I'm going to introduce to you our paper, Metamorphic Testing of Deep Learning Compilers. I'm Dongwei Xiao from the Hong Kong University of Science and Technology. First of all, let's take a look at the background of our paper. Nowadays, we have various deep learning frontends, such as TensorFlow, PyTorch, and Onyx. We also have various hardware backends, such as GPU, CPU, and FPGA. However, deploying the deep learning models from the front ends to the back ends is non-trivial. For each possible pair of front ends and back ends, we need to define a strategy to deploy the front ends to the corresponding hardware back ends. This process requires great engineering effort. Thankfully, we have deep learning compilers. For deep learning compilers, we only need to take the model specification in the front end, compile it, and the compiler will generate the corresponding executable code for the various hardware backends that we want to run our model on. There are several industry-level deep learning compilers. For example, the TVM from Amazon, Glow from Meta, and also XLA from Google. The deep learning compilers typically contain a quite complex workflow. They take the model specification in the deep learning front ends, such as PyTorch, and then translate it to the high-level intermediate representation, and then to the low-level intermediate representation, and finally produce the executable machine code of the corresponding hardware backends. The compiler may do several rounds of optimizations in between. However, this complex pipeline may contain bugs in the middle. When the deep learning compiler bugs are quite difficult to be noticed. For example, when a user notices that his or her model isn't working, he or she may doubt that whether the model is badly trained, but he or she won't be able to guess that the failure of the model is in fact due to a deep learning compiler bug. Now the question is there any automatic way to detect the deep learning compiler bugs? Well, you may think about a naive way for doing so. First, you take the deep learning model specification and run it with input, and for example, this image cat, and through the deep learning frameworks such as TensorFlow, and you get an output O, which in this case is the classification probability of cat and dog. At the same time, you take the deep learning model, compile it by deep learning compilers such as TVM, and get the deep learning executable. You execute the executable with the same input as the deep learning framework and get the output O prime. O prime is also a classification probability. Then you compare whether O prime equals to O. If the O prime is not equal to O, then there is a bug in the deep learning compiler. However, this approach doesn't really work. Why? Well, it is due to the different floating point representations of deep learning frameworks and compilers. For deep learning frameworks, they wrap floating point numbers in object, whereas the deep learning compilers use floating point machine code to represent floating point numbers. The two different floating point representations introduce floating point deviation across the output. And by our experimental results, the output of the deep learning frameworks has a 10 to the order of -2 difference compared with the deep learning output of the deep learning compilers. Therefore, even though you observe that the output of the frameworks and compilers are different, you cannot say that it is due to a bug in the deep learning compilers, because it may also be due to the inherent floating point deviation problem. So, but how is it possible to alleviate the floating-point deviation problem? Well, the answer is yes. If you do not compare the deep learning compilers with deep learning frameworks, then there is no such thing as two different floating-point representations. So the floating-point deviation problem can be greatly alleviated. But you may wonder, how can a compiler be compared with itself? Well, this is what we do, and I'm going to introduce the method. The basic idea behind our approach is that equivalent deep learning models should be compiled to equivalent executables when they are being compiled by the compiler. Here we mean equivalent by saying that they produce the same output under a given input. The figure below illustrates our pipeline. First we get two equivalent deep learning models, M and M prime. We compile the M and M prime with the deep learning compiler that we want to test, and get two executables, E and E prime. We execute two executables with the same input and observe output O and O prime respectively. Then we check whether O equals to O prime. If O does not equal to O prime, then it means there is a bug in the tested deep learning compiler. But the challenge is, how do we produce two equivalent deep learning models? Well, this figure illustrates the basic the strategy that we use. Basically, we're using mutation. We start from a seed deep learning model M, and we randomly choose a target operator in the computation graph of M. In this case, we illustrate it in green. And we mutate the target operator to get a new set of operators, which is on the right-hand side. By doing so, we get a new model N prime, which has the same computational graph, except in the green part. The only constraint with our mutation is that the mutated model M prime should produce the same output of its original model M, so that M prime is equivalent to M. Now let's take a detailed view of how do we mutate the target operator into a new set of operators. First, we take the target operator and we introduce a guard node, which always outputs 0. We also introduce a set of dead code node and multiply its output with the output of the guard node. We then add the result of multiplication to the output O and get a new output O prime. We can see that what this structure computes is basically O prime, which is equals to O plus 0 times the output of that code. Well, it is easy to see that O prime is equal to O, which means that after inserting this structure, the mutated model has the same output as the mutation before. There are two crucial parts in this structure. The first is the guard node, and the second is the dead code node. First, let's take a look at how to generate a guard node that always outputs 0. Well, the only constraint of the guard node is that it should output 0. We introduce two guard condition generations. The first is the universal obscure conditions, abbreviated as UOC. The second is the per input obscure conditions, abbreviated as PIOC. Let's take a look at UOC first. We start with randomly selecting two operators, A and B from the computation graph of the deep learning model that we want to mutate. Next, we multiply A and B with themselves. We also multiply A with B with -2. Then we sum up all the three items and negate the summation result and go through a ReLU unit. So the overall computation of this structure is that is a ReLU of the negation of A squared minus 2AB plus B squared. By utilizing the math property, we can see that no matter what the value of A and B is, A squared minus 2AB plus B squared is always greater or equal to 0. So the input to the ReLU is always less or equal to 0, which means that the output of the ReLU is always equal to 0, no matter what the value of A and B is. The second generation strategy is the per input obscure conditions. Per input obscure conditions, as its name suggests, is closely related to the input. We take a randomly selected input and feed it to the deep learning model and run a forward inference. At the same time, we profile the output of the target operator when the model is doing forward inferencing. For example, we record that the output is 0.3 when the input is this tabby cat image. Next, we introduce a constant node whose value is also 0.3. And we subtract the constant node's output from the output of the target operator. Therefore, the output is 0. But notice that the output is 0 only when we choose that particular input. So this is where the name per input comes from. Well, by far we have seen how to generate the BART node. The next question is how do we generate the dead code node? Well, if you notice that the output of the dead code has no effect on the final output because its output will be multiplied by 0. Therefore, we are free to choose any kind of operators as the dead code node. We choose 5 representative kinds of operators: add, subtraction, multiply, convolution, and linear. We by far we have seen how to mutate the seed model and get its equivalent model M1, but this is only mutation for one time. In order to further stress test the compiler, we applied the mutation strategy multiple times and iteratively so as to get a larger, more complex model than the original seed model. Now, let's take a look at the experiment and the results of our paper. We tested 3 deep learning compilers: Amazon from the TVM from Amazon, Go from Meta, and XLA from Google. We used 3 deep learning models as the mutation seed: the ResNet 18, VGG 11, and MobileNet. We mutate each seed deep learning model for 1,000 times with 5 different random seed numbers. This table illustrates the complexity of the seed and the mutated deep learning models. The seed models typically contain less than 100 operators in its computational graph. In contrast, after mutation, we can get a model with over 10,000 operators, which is much larger than the original seed model. Therefore, we can greatly stress test the deep learning compilers. By the testing campaign, we discovered 1989 compilation failures in all the three compilers. We also discovered 435 erroneous compilations. Here we mean erroneous compilations by saying that the compilers successfully compiled the deep learning model into the executable, but the executable is wrong. Furthermore, we use 148 hours to investigate the root causes of those failure cases. And with the help of GDB and IDA-Pro, we located 4 bugs in the deep learning compilers that account for all erroneous compilations. Here's an example of our discovered deep learning compiler bug. The produced deep learning compile executable, when it is doing forward inferencing, it may use some temporary buffers for storing the intermediate computational results. However, one buggy situation is that those temporary buffers override the other buffer that is currently used by other operators. Therefore, this stealthy buffer override will result in the wrong model output. And that's all. Thank you for listening. I'm happy to be contacted through my email. And wish you a good day. Now I'm glad to take any question. Thank you.